Hello everyone. Good afternoon from London. My name is Kalkidar, and thank you so much for giving me this amazing opportunity to present my work. And starting off with what exactly my work is, it is about enhancing handwritten music sheet datasets using GAN architectures. And I work this along with my supervisors, Elona and George from Queen Mary University of London. So over the course of this presentation, I'll be talking about what exactly the main motivation for my work was and what were the related works that were done to address the same challenges, the different kind of data sets that were being used, the pre-processing steps. I'll also be giving an overview about the various model architectures that I tried to experiment with, as well as the approach that I took for evaluation, finally, the results and conclusion. So we know that OMR systems showcase a really good performance when they're dealing with printed music scores, but they do not really match up to the same level of performance when it comes to handwritten scores. And that serves as a primary objective or a primary motivation for this research. And that also stems from two main challenges that are showcased by handwritten sheet music data. One is there is a tremendous scarcity of handwritten music data that is available at the moment. And also we have very diverse and complex handwritten styles. So in order to address this, we decided to use advanced GAN architectures to be able to synthesize handwritten music sheet data. So I just want to start off by acknowledging the fact that there have already been several existing works that did try to address this very challenge. Like we have Mash Schema, the synthesizer, and it's really good to know on a side note that there's also Smash Schema in the pipeline, and I'm sure that it's Smash Schema is going to absolutely smash it. And also, we have autoencoders as well, and we have also seen a more recent work which utilized a cycle GAN. So another objective for this project is to improvise the existing cycle GAN implementation that is already done in order to achieve a better style transfer. So finally, we also can take a look at the results and we can try to analyze and compare the image generation class of GANs with the performance of the image to image translation class of GANs. So moving on to the data sets that were being used. So we know that GANs work in an unsupervised manner when it comes to generating anything. So first we have the image generation class of GANs, let's say deep convolutional GAN or progressive GAN or style GANs that just take a look at one data distribution and then they try to model or mimic that data distribution in an unsupervised manner. So for that purpose, we need a handwritten data set. So CVC Mu Schema is one of those publicly available handwritten data sets that has a really good diversity of handwritten style, which has around 1,000 music sheet images. And these 1,000 music sheet images were written by 50 composers, where each composer transcribed 20 pages each. And for the image to image translation task, that is also an unsupervised learning task where the model is trying to learn the mapping between two domains. One domain is, of course, the handwritten domain, and the other one is the printed domain. So in order to model the data for the printed domain, we have used the DOREMI dataset, and that consisted of 6,432 music sheet images in the printed style, but we considered only 1,000 images in order to match up a similar distribution as the handwritten domain. So moving on to the pre-processing steps, a major challenge that a lot of GANs display nowadays is that the inputs to all these GANs have to be square dimensional images. They can't be rectangular images. So what we try to do is first we have a lack of availability of our data. And on the other hand, we also have this constraint that we need only square inputs for GANs. So we took the rectangular dimension of all the staff images. We applied pre-processing steps to convert them to individual crops, squared crops, and resized all of them to 350 cross 350 dimensions. And this increased the size and variability of training data, as well as making our training data adaptable to be passed as input to GAN architectures. So giving a broad overview of the model architectures. So first, we wanted to establish a baseline model. And deep convolutional GAN is a very common baseline model that is used when it comes to image generation tasks that we see nowadays, not just in the music domain, but if we see other domains as well, like medical image generation or satellite imagery and so on. And we also wanted to establish a more advanced GAN architecture, like a progressive GAN, which tries to mimic the way humans try to learn. And it is also a GAN that showcases image generation with improved quality, variation, and stability. Finally, we wanted to compare the results that we obtained from these two GANs with, let's say, cycle Wasserstein GAN, which is like a modified version of cycle GAN. So CycleGAN is like a state-of-the-art image-to-image translation network. And the main advantage of a CycleGAN is that it doesn't really require the need of any paired training data. So, uh, and Cycle Wasserstein GAN is just the modified version of the CycleGAN. Speaking a little bit in detail about the methodology of a deep convolutional GAN. So as it is common with any GAN architecture, we have two major components, the generator as well as the discriminator. So the generator tries to take a random noise vector as input, and it tries to upsample that with different convolution layers to finally produce a generated fake image as an output. And speaking about the discriminator, it takes two inputs. One is the image generated by the generator itself, and it also takes another image from the real distribution of data, and it computes a scalar output, let's say if it's a real or generated image. So one challenge that we were facing while implementing DC GAN was that the discriminator was becoming overpowerful, and the generator was not uh, capable of learning as quickly as the discriminator. So we identified a technique of label smoothing where we tried to not pass hard labels, but rather smoother version of labels for real images as well as fake images. This improved the training much, much better, where the discriminator tried to show great stability in the training process, which can be seen in the training loss here. So moving to progressive GAN. So we as humans, we have a way of learning things, right? So we start to learn things that are much simpler. Then we try to progressively learn more and more complex tasks. It's essentially the same process when it comes to training a progressive GAN as well. So the progressive GAN first tries to learn how to output a 4x4 image, an image with very less spatial resolution. Then it tries to learn how to generate an 8x8 image and so on till a higher target resolution that we want. So even in a progressive GAN, we have the generator component as well as a discriminator component. And in the generator component, we have applied several concepts that helped in greatly stabilizing the training. So the first one was dynamically weight scaling and achieving an equalized learning rate. So as the model tries to go through this progressive process of training, we try to introduce additional layers, and we don't want one layer to learn quickly than the other layer. So we want to achieve sort of like an equalized learning rate across all the layers. And we also used pixel normalization over the traditional batch normalization, and we applied a fade-in mechanism as well. So discriminator, on the other hand, tries to downsample the input in the reverse order. And we also applied an interesting concept called mini batch standard deviation. Now, the reason why this was important for us is because in mini batch standard deviation, you capture the batch level statistics that are passed as additional input to the discriminator, which also enhances the final diversity of the output images that you are able to derive from your GAN. So talking a little bit about the methodology of the loss functions and the training of the progressive GAN. So we can observe that as the training progresses towards higher resolutions and higher epochs, there is a lot of oscillation and instability that occurs. This is mainly because of the challenge that displayed by higher resolution of images. So as the images resolution gets increased, we have to decrease the batch size to optimize the training process. Now, as the batch size gets smaller, these batch statistics are no longer efficient in order to have like a good training process. Now, coming to the another interesting aspect of image-to-image translation, which is a cycle Wasserstein GAN. So the main difference between a cycle GAN and a cycle Wasserstein GAN is that the adversarial loss that is computed at the discriminator stage, it is estimated using the Wasserstein metric and not the traditional GAN loss metric. So we have two major domains. We have domain A, which is the printed scores, and domain B, which is the handwritten scores. So generator G tries to take an image from the printed score and it translates that to its corresponding handwritten version. And D1 takes that as input, and it also takes another input from the handwritten scores, and it tries to compute the Wasserstein adversarial loss. So with this, half of the cycle is done, which is the forward consistency. And the other side of the cycle tries to do the same with a different generator and a discriminator component. So essentially, in the total methodology, we have two Wasserstein adversarial losses as well as one total cycle consistency loss, which is showcased here. And we can also control the importance of cycle consistency loss using a hyperparameter. So another challenge that we faced while training cycle Wasserstein GAN is the increasing trend of the generator losses, which we were not able to control. But the discriminator was becoming overpowerful compared to the generator. So we use several evaluation metrics, both quantitative as well as qualitative, in order to analyze the results that we got. So uh, quantitative evaluation in GANs is an ongoing research topic, and it is a challenging aspect of evaluation. So we did not want to rely on only one quantitative metric, but we use several of them. So the quantitative metrics that we use were inception score, Frechet inception distance, and kernel inception distance. Now, kernel inception distance offers an advantage over Frechet inception distance because it is an unbiased estimator. It is non-parametric and doesn't really assume your distribution to follow a Gaussian shape or as such. And looking at the results over here, we can say that from at least a quantitative perspective, cycle W GAN and progressive GAN perform much better than DC GAN. And taking a look at the actual images generated themselves. So we have used a pre-trained object detector to be able to identify objects from each of the generated images. So progressive GAN shows a very interesting aspect in the generated images where it tries to generate consistent staff lines as well as a good mix of symbols, a good diversity of different kind of musical symbols being present in the images. And it's a similar case with cycle Wasserstein GAN as well. Now, we wanted to compare the results that we got with cycle Wasserstein GAN with the previous work of cycle GAN. And we can see here the comparison of the translation process itself. So we can see the printed score and its corresponding translated handwritten version. And we can identify that cycle Wasserstein GAN showcases a better style transfer, which closely resembles the handwritten style compared to the cycle GAN. And there are still some inaccuracies in images generated by both cycle GAN and cycle Wasserstein GAN as well, especially several gaps in the images. But we also wanted to take a deeper look at how successful our style transfer process actually was. So we wanted to take a deeper look at the distribution of the real handwritten images, the real printed images, as well as the images generated by the cycle W GAN. So taking a look at the principal component analysis in a reduced 2D feature space, we can see that the shape and the direction of the cycle Wasserstein GAN is closely resembling that of the real handwritten images compared to a completely different distribution showcased by the real printed images. And this is even indicating the same thing in the histogram distribution as well, with a similar peak and a similar spread in the histogram plots of both the principal components. So the conclusions for this finally are that progressive GAN showed interesting results with a good bunch of diversity in generating images, and cycle Wasserstein GAN achieves a better translation compared to cycle GAN. However, we want to acknowledge that there is still refinement required when it comes to hyperparameter tuning and a better training process in order to stabilize the generator losses. And future work can take different directions from here. So the first one is image in painting. So we can see that there are several gaps identified when you try to translate the printed image to the handwritten score. And we can try to use image inpainting techniques to address this. And so far we have seen something called unconditional generation. Basically, we are telling our GAN model, like a DC GAN or Pro GAN, to generate whatever it wants. So we can't really condition or target the generation process. We can't really say that, okay, I want a clef in my image or I want a sharp in my image. So we can try to achieve conditional generation as well. And diffusion models and MLLMs are definitely being talked about quite a lot in today's age, and that can be explored as well. In fact, it was quite interesting that in an earlier presentation, the question that was asked is, can MLLMs be used to recognize music images? But a similar question can be asked if they can be used to generate music images. So I hope you have enjoyed my presentation. Thank you so much for your time. Yeah.
Thank you very much. It would indeed be great if we can just generate as much data as we want. Yeah, fine. Please go ahead.
I have a question about the progressive GAN. You told that you have changed the resolution from low resolution to high resolution. Did you also try to change it from simple, clear pictures to more difficult pictures, the progressive version?
Could you please clarify what you mean by simple pictures and more difficult pictures, just so that I can understand?
I mean, if you translate the music version, then and it's handwritten, I think there are more simple examples where you can easily detect what should be translated, or is this more difficult because it is written in not so a good style, and you could start with those which are particularly clear and then give more difficult pictures.
That is definitely an interesting aspect to think about. So we certainly did not do that. So the approach that we took while training the progressive GAN was to progressively teach the GAN how to extract features based on the resolution alone. So if the model is being exposed to a lower spatial resolution, it can only identify a limited set of features compared to if it is being exposed from to a higher uh, spatial resolution. But that learning process takes time. So to answer your question, it was just the resolution that we considered during progressive training.
Okay, thank you.
Okay, go ahead.
Can you just correct me if I understand, or just if I understand it correctly, to train this model, you just have two piles of images. One of them are handwritten and one of them are printed. And then you run the training process and you get this, right? You have no more, you don't have alignment between them, like content-wise. You just have like, here's a bunch of printed images, here's a bunch of handwritten.
Yeah, so I believe this is for the cycle GAN or cycle VAS16 GAN for image-to-image translation.
Yeah.
So we don't really have any sort of predefined mapping between the source domain and the target domain, because cycle GANs and cycle W GANs try to learn the mapping inherently during the training process. So they don't require any sort of paired annotated training data as such. So.
I would be really interested to see what happens if you give it not CVC new schema kind of images, but more like the colorful images that are the scans from libraries. I'm like curious what happens with the background and with the different shapes. Like how that.
Yeah,
I don't know if it's like only black and white or if it can handle like RGB color space.
It can definitely handle RGB values as well. But for the purpose of my experiments, I try to transform all of them to grayscale so that I can make the training process much faster and efficient. But it can certainly handle RGB as well. And
because it's starting to look way better than last year. Like now it's not just like style-ish transfer. Now it's like truly style transfer.
right, yeah, yeah.
Thank you.
A question from my side. Maybe I didn't patch it fully. The output of the GANs, what are the dimensions of this thing? So are you kind of just creating these small patches, or can you actually create larger, like a whole stuff or even a full image?
Right. So the GANs take square patches as inputs, and they also output square patches as outputs. It's because they are trying to model the distribution, which has square patches of inputs throughout. So for the purpose of being able to upscale this or reconstructing an entire stuff itself, so there is one post-processing approach that we can take with the images that we can get with, let's say, a cycle GAN or a cycle Wasserstein GAN. So we have, let's say, a printed stuff to begin with. We try to break the printed stuff into square patches. We try to convert each square patch into its translated version of handwritten patch. Then we can apply post-processing to get a handwritten stuff. So that could be one solution to go ahead with.
Right. Attends?
Yes, just to follow this question, what happens at the joining patches? Don't you have any strange effects between two connected patches?
So I want to preface by saying that I did not do the the post-processing, and I did not do the reconstruction of the entire rectangle itself. But there is, I think there should be a possibility of introducing any unwanted artifacts when you're trying to combine two patches. There should be. You're right.
Okay.
Yeah, I have
But
some.
otherwise, just to add to that, sorry, it would be that the staff line positions would be the same. So if we look at all the patches that we generated from the one model, so as he was saying, if we use one image, patch it up, and then, you know, come back again together. So since you would have the same spacing of the staff lines, you would be able to patch them back depending on that staff line where they meet. But you would probably have other elements maybe that would be artifacts, but I think from the cycle Wasserstein GANs, it would be all right. It wouldn't be a big problem.